So in the last video, what we talked about was kind of our standard problem-solving method for problems like this. So we're going to be looking at the same problem as we did in the last video. If you haven't seen part 1, go back and watch that before you watch this, part 2 of pumping a liquid. So we're going to start with the same problem. Just for a quick review, what the problem is, we have a liquid which is coming in at 60 degrees C, a quality of 0, so it's saturated, and we're bringing it up to a pressure of 3 megapascals. How we solved this problem in part 1, we did our energy balance. That simplified energy balance was delta H equals minus WP. Once we simplified our energy balance, we said, aha, this is adiabatic and reversible. That tells us that this is a delta S equals 0 process. We could find H1, the initial enthalpy. We could find that from our tables. That was 251.11 kilojoules per kilogram. Then we could find H2 from our tables, which was 254.1 kilojoules per kilogram, or something thereabouts. When we had to find it from steam tables, we had to use a double interpolation, which was a little bit cumbersome. We could do it, but it wasn't ideal. Or we could use something like Cat3 in order to find that. I apologize. Okay, and then we could go back and we could use our energy balance and we could calculate what the work was. In this case, it was minus 3.01 kilojoules per kilogram. Okay, so this is one way of looking at the problem. Kind of the more traditional energy balance perspective. I guess I saw more traditional because traditional, at least in the context of this class, not necessarily more traditional or more usual, but how we've typically solved these types of problems. We're going to look now at a different way to solve it, and it's nice because it's less interpolation. That's going to be especially nice for exams, where interpolation, we're going to be using our steam tables and not Cat3. So I'll write here this problem-solving method is especially nice for exams, and also gives a visual understanding. So this is going to be more graphical and more visual, or easier to think in those terms. And we'll really kind of set the stage for some of the stuff that we're going to do in the, I guess, mid-second half of the semester. So maybe 3/4 of the way through the semester. So a little ways out, but this will set the stage for some of that. So we're going to think a little bit in this about what work is. Right? Work is a force applied over a distance. It's force times distance, which in the case of an ideal expansion or compression, right? Ideal, let's define what that means. So this is adiabatic, reversible, change in kinetic energy is equal to 0, and the change in potential energy is equal to 0. So if all of these things are true, right, which isn't that much of a stretch, these are the same things that had to be true for our analysis, where we did kind of our more usual analysis. We needed the same things to be true in order to do right? To simplify our energy balance like this, we said that potential energy and kinetic energy were 0. Adiabatic and reversible, that was delta S equals 0. So it's the same assumptions, the same things that need to be true. Anyway, so if these things are all true, as they were before, then our work for a reversible process can actually be thought of as just the integral from state 1 to state 2, and that's actually negative of the integral of specific volume d pressure. Specific volume and pressure, right? Think about how this looks. A force applied over a distance, force, that's pressure. Applied over a distance, that's where specific volume comes in, right? Pressure is really a force over an area. Specific volume is like a meters cubed type thing. Volume is a meters cubed type thing. So we have a force divided by meters squared times a meters cubed, so force times a distance. Let's think graphically what this integral is telling us. And let's think first about a gas turbine. So in a gas turbine, we start somewhere at high pressure and high temperature. So let's say this is the inlet of our gas turbine. We're relatively high on this pressure volume graph. And we're at relatively high specific volume because we're a gas and we're at high temperature. Right? So specific volume goes up. If we're a gas, it also goes up as temperature goes up. As we go through our turbine, we're going to be going to lower pressure. We're going to be expanding. So we go down through a curve, maybe something like this. Okay, from high pressure, high temperature, we expand. As we expand, right, the gas is going to expand to a higher specific volume. The integral that we had here, and I'll box this because that's going to be an important equation that we're going to use. The integral that we have there is, right, that the work is going to be equal negative the integral of volume d pressure, right? An integral is just an area under the curve. So what that integral is saying is that this area here is the work of our turbine. Right, for a turbine, we're going to be extracting work, so that would be a positive value. But the magnitude of it is just simply that area. Now let's think of what's happening with a pump where we're pumping a liquid. When we're pumping a liquid, we're coming in at low pressure and we're leaving at high pressure. We're a liquid, so we're somewhere down here. So we're coming in here at low pressure, low specific volume. As we increase the pressure, our specific volume hardly changes. It does change. It changes a little bit. As we go up to a higher pressure, the volume will actually decrease a little bit, but not a lot. So we're almost perfectly vertical. And then this case here, right, similarly, that area is the work of our pump. So there are a couple things that we can kind of, just put both of these on the screen at the same time, there are a couple things that we can note when we're looking at this. One, how we fit on a pressure volume curve is kind of directly related to the work that's happening. We can say a couple different things about liquids and gases. For gases, right, a high specific volume leads to large work. And then conversely, for liquids, we have a low specific volume means small work. So if we think of our system, say like a Carnot cycle, where we have a gas expanding across a turbine and then a liquid being pumped, or a Rankine cycle rather, where we have a gas expanding across the turbine, a liquid being pumped to higher pressure. The reason that the pump takes less energy or takes less work than the expansion gives us is because that we have these two different specific volumes. Likewise, for Carnot, right, where we have a gas on both sides, the compression is done at lower temperature, which is a lower specific volume. The expansion part, the turbine, is done at high temperature, which is a higher specific volume, which is why we get more work out of the turbine than we put into the compressor. The other thing that we can say is that right, for a gas, both temperature and pressure change the specific volume. So specific volume is a function of temperature and pressure for a gas. For a liquid, it's not. So specific volume is a weak function of temperature. And you can go, and I encourage you to go back and look at some of your steam tables and actually check out how this works. Look at the specific volume at a single pressure and look at how does that change as you change the temperature of the liquid. It will change a little bit. How does that change for a gas? Go to the superheated vapor tables where we have just a normal gas. Look at how temperature and pressure affect specific volume and comparing gases and liquids. So specific volume is a weak function of temperature for liquids. Specific volume is nearly independent of pressure. So temperature matters a little bit, pressure matters even less. It does matter, but it matters less. So for an ideal expansion or compression, for any gas or a liquid, right? That's the equation that we had before, where the work reversible equals, negative the integral from 1 to 2 of specific volume d pressure. If we have an incompressible liquid, right? An incompressible incompressible means that that the specific volume is constant with pressure. Really means that more things than just the specific volume is constant with pressure, that the properties of the liquid are constant with pressure. So really, all properties, other than the pressure, of course. But what that means is if we take a liquid, right, and we know this from our everyday experience, if you take a gas and you, say, fill a balloon with gas and you squeeze on it, the gas will contract. If you pull on a gas, you can expand the gas. If you have a liquid and you press on it, it doesn't really change. It's kind of like a solid, right? If you press on a solid, there's no discernible change in the volume of that solid unless it's a squishy thing, right? But if it's a hard solid, it will behave kind of like a liquid does, where you press on it and nothing really happens to the volume. It's not squishy, it's incompressible, which is very different than a gas. And that's what we're talking about here. We're talking about something that, in the ideal case, you press on a liquid, that liquid doesn't change properties. It is considered incompressible. Now, liquids are not exactly incompressible. When you press on them, they do change properties, but they only change a little bit. So to a first approximation, we can often consider that they are, in fact, incompressible. And we'll do that a little bit here. But if we imagine what's happening to this top equation here, if we have an incompressible liquid, that means that the specific volume is constant. If that's a constant, we can pop it out of the integral, and we get simply that the reversible work is equal to minus the specific volume now times just the integral of dp, which is just becomes delta p. So what this says is that the reversible work, so the work for this ideal pump for an incompressible liquid, is just the specific volume times the change in pressure. Let's go back to our problem and just see what that actually looks like when we throw in some numbers and make sure we get the same answer as we did before. I went through and just wrote down some of the properties of the incoming stream here, stream 1. And we're going to find really the key properties for this second stream, stream 2, just like we did in the last example, except this time we're going to use this equation for an incompressible liquid. Okay, so we're going to say we do know something about the process. We know that this is an ideal pump. So we know ideal pump, which means it's reversible, means it's adiabatic. It means that there's no change in potential energy, no change in kinetic energy. So that packs quite a few things in it. But we know that it's an ideal pump, and we also know we have an incompressible liquid, or an approximately incompressible liquid. Okay, if that's the case, then we can just simply kind of skip all of our interpolation steps, skip all of the, let's write the entropy, say delta S equals 0. We can kind of skip all that, and we can jump right to calculating the work. So then the work of our pump equals specific volume delta capital P for pressure. You can see I'm just rewriting the equation up there. I just threw the negative sign on the other side by the pump. So then our specific volume is 0.001017 meters cubed per kilogram. And now our delta P, this would be P2 minus P1. So P1, again, this is a value I looked up. It's the saturation pressure. So what's the, so 19.94 kilopascals. That's the pressure that we looked up in our tables. Pressure 2, that's our 3 megapascals. So we have to do a little bit to make sure our units work out. So let's make sure that those work out. So our units, we have minus W pump equals 0.001017 meters cubed per kilogram times, so 3 megapascals, that's 3,000 minus 19.94 kilopascals, which is kilojoules per per meter cubed. Okay, so a kilopascal is a kilojoule per meter cubed. That's just a standard unit conversion. We can plug in these numbers. You can see our numbers will work out pretty well. The meters cubed will cancel out, our units will work out well, and we'll get 0.001017 times the quantity 3000 minus 19.94. When we do that, our pump work is 3.03 kilojoules per kilogram. And then we can go back if we want to, and we can use our energy balance to find the enthalpy. So we could use our energy balance and do something like this, because our energy balance still works. So we would have the same energy balance that we did in the last example, which would lead us to H2 equals H1 plus WP. Right, think about what this equation means. That means that the enthalpy that we have coming out is equal to the enthalpy that we had coming in plus the amount of work that we put in. So really that the work that we're putting in is right, because of conservation of energy, that work has to go somewhere. So it's really being converted into thermal energy or being converted into an increase in enthalpy. So this would give us an outlet enthalpy of about 254.14 kilojoules per kilogram. And if we go back up to some of the numbers that we got from the previous way that we did that, we got a work of minus 3.01 compared to 3.03, so within 1%. And we have now an enthalpy of 254.14 instead of 254.1. So we get essentially the exact same answer both ways, because this assumption of incompressibility is actually a really, really good assumption for most liquid cases. So often we can use kind of either of these methods interchangeably. They both get us to the same answer. The second method, though, right, kind of calculating the work directly, often is easier. It's nice for systems where we have liquids, where we can make this assumption of incompressibility. We could use the same equation as I showed here to calculate things for a gas turbine, but we would need to do a little bit more creative integration, because we can't make this assumption of incompressibility where we have just a straight vertical line. We're really, right, just measuring the area of a rectangle. We have, a curve on one side for a gas turbine. So we'll continue to use this, and hopefully we'll use some of this same stuff, especially this equation of reversible work. We'll continue to use that later in the course. But hopefully you find this helpful in thinking through a little bit how we can look at the same problem in multiple different ways.